All right, today we discuss a last important topic on our treatment of discrete random variables, which is the independence of random variables. But before that, let's make a small correction to a mistake made in the previous lecture that many of you noticed but didn't warn me about. Okay, so let's revisit that topic. We were considering a binomial random variable, let's call it B. A binomial random variable can be characterized as a sum of independent Bernoulli random variables, right? So in particular, if B is binomial with parameters n and p, this means B can be written as the sum of xi's, where xi's are Bernoulli with parameter p and independent of each other, and there are n of them. Okay, and we were computing the expectation of this clearly using the linearity of expectation. The expectation of the sum of this sum is the sum of the expectations, which is what, Burak, do you remember? N times p. But Burak's question was, is this also equal to the summation k times n choose k, p to the k, 1 minus p to the n minus k? Right, that's right. Okay, what are the limits for k in this summation? K goes through all the possible values that the random variable B can take, which is 0 to what? N. Okay? Any problem with this? Is it now correct? Okay. We can start our discussion of independent random variables now. Previously, in the previous hour, we defined what it means for a random variable to be independent of an event. Okay, and two random variables are independent if the probability that x equals x and y equals script y can be written as the product of the probability that x equals script x and the probability that y equals script y. Okay? We actually wrote this last time. And it follows from this that the joint PMF, the joint PMF in general, when two random variables x and y are independent, the joint PMF breaks into the product of the marginal PMFs. Okay? Another consequence is that when x and y are independent, the expected value of x times y is equal to the expectation of x times the expectation of y. Okay? So I believe we proved this last time. Is that clear for everyone? Okay. Just like expectation, we can consider any function of x, g of x, and any function of y, h of y. Okay? And g of x is independent of h of y for any g and h. Why? G of x is a function of a random variable, so it's a random variable itself. H of y is a random variable itself, and they are defined on the same probability space. So we can talk about the joint distribution of g and h, and they are independent because x and y are independent. Okay? So intuitively, if x tells us nothing about y, a function of x can not tell us anything about y or a function of y either. Okay? Let's move on to the topic, the new topic of today. consider the variance of the sum of independent random variables. Okay, so everybody remembers the definition of variance, I hope. So let's consider the variance of x plus y, okay, where x and y are independent. So how do we proceed? We just use a definition of variance. The variance of x plus y is the expected value of x plus y squared minus the expected value of x plus y whole thing squared. Okay. What's next? So far we have not used independence, so let's erase this expression. Okay? So this is true in general for any two random variables x and y, right? The variance of x plus y equals the expectation of x plus y squared minus the expected value of x plus y squared. Okay, so let's expand the summations. This is x squared plus 2xy plus y squared. And this is, what do we do for this one? We use the linearity of expectation to write it as expected value of x plus expected value of y squared. Okay, what did we use here? We used linearity. So far we have not used the independence of x and y. Okay, let's keep using linearity again. Let's use linearity here. The expectation of the sum of these terms breaks into the sum of expectations. Expected value of x squared plus 2 expected xy. What did I do here? The constant 2 moved out of the expectation. Okay? Plus expected value of y squared. What's next? Minus expected value of x squared minus 2 expected x, expected y, minus expected value of y squared. Now what do you suggest that we do? Maybe combine these two terms. Let's combine these two terms and say expected value of x squared minus expected value of x squared plus, and combine this term with this term, expected value of y squared minus expected value of y squared. I'm doing this really slowly such that so that everybody can really follow it. And we have one final term left, which is twice the expected value of xy minus expected x times expected y. Okay. So far, I have just used the linearity of expectation. So what we've done here is valid for any two random variables x and y. What is this? That's the x. That's the variance of x. Yeah. Is there a question? Yes. So we will use that in the next line. So far, basically, first I want to write an expression that's valid for any two random variables before we use our independence assumption. Okay, so this is the variance of x. This is the variance of y. And we have this term. Okay. So, as you pointed out, what was your name, please? As Selin pointed out, this term is equal to 0 when x and y are independent. Okay. In general, this term may be positive or negative. Okay. Also, this term being 0 does not imply that the random variables are independent. Okay? So basically, let's write our conclusion. Our conclusion is that when x and y are independent, the variance of x plus y is equal to the variance of x plus the variance of y. Okay? So this is something to really remember because it's very useful. Also think of what variance means intuitively. Variance is a measure of how random something is. When is variance 0? There's only one condition under which variance is 0. When the given random variable is actually a constant, when it's not random, when it's equal to a constant with probability 1, only then variance is 0. Okay? The larger the variance, the more randomness. Now, when you add two random variables, their variance builds up the most when these two random variables are independent. Okay? So it makes sense that when they're independent, their variance builds up. Think of a very simple case when x and y are dependent. Okay? Let, for example, y be equal to negative x. What happens to the variance of the sum? Y is equal to negative x. When you add them, you get 0. Okay? And the variance is 0. Okay. So here's another maybe more illuminating example. Oh, wait. Let's do one more step. Let's repetitively use this result for more random variables than 2. Okay? So in general, if you have 3 random variables, what happens to the variance of the sum? Let's show that. Variance of x plus y plus z, okay, is equal to the variance of x plus y plus z. Okay, x plus y is a random variable, z is a random variable. We can treat these two as 2 random variables, right? Now, if x, y, and z are independent, then x plus y and z are independent. So this is the variance of x plus y plus the variance of z. Okay? But we already know that the variance of x plus y is variance of x plus variance of y. So we reach the conclusion that in general, when you have n random variables, the variance of the sum is the sum of the variances. Okay, any question about this? Okay, so let's do an example. During April in Ankara, it rains with probability p each day, okay, independently from day to day. Compute the variance of the number of rainy days in the whole month of April. Consider how this variance changes with p. So let's erase this part. What do you think? What do you think the answer is? Huh? Okay, how do you formulate this problem? Is there a question from an earlier part? No? Okay. So, how do we formulate this problem? Right. So this is a binomial, right? N times P. So so basically, in the example, N is 30 because there are 30 days in April. Okay. So the variance. Wait. You told me the expectation.
Yes.
But the question is asking for the variance. Anyway, so the expected number of rainy days is 30p. You're right. Okay. Let's let the number of rainy days be b. Okay. Remember, b is a binomial. Each day it rains or not with probability p independently of every other day. I goes from 1 to 30. What is the variance of b? The variance of b, now we're going to use what we just proved. The xi's are independent, so the variance of the sum is equal to the sum of variances. Okay? Any problem with this? Now, each day has equal probability of rain. So the xi's have identical distributions. Okay? The variances of xi's are equal. So we can just say this is 30 times the variance of x1. Right? 30 times the variance of x1. What is the variance of x1? Variance of a Bernoulli. How do we compute that? The variance of x1, expectation of x1 squared, what is that? x1 squared is 1 if x1 is 1 and 0 otherwise. So x1 squared is 1 with probability p. Expectation of x1 squared is p minus expected x1 squared, which is p squared. P times p squared, which is p1 minus p. That's the variance of a Bernoulli. Okay, so this is 30 times p, 1 minus p. Let's plot this as a function of p. Let this be the p-axis. The possible values of p live between 0 and 1. What is the variance when the probability of rain is 0? What does this mean, probability of rain being 0? Rain is impossible. It will, rain with probability 0. So the number of rainy days is 0. What is the variance of that? 0. Okay, because it's a constant. So let's say this is the variance of the number of rainy days. How about for 1? 1 means the probability of rain is 1. So the number of rainy days is equal to 30. It has, again, 0 variance. It doesn't vary at all. It's a constant. So the variance reaches its makes its 2 zeros at the 2 extremes where p is 0 and 1. In between, it behaves like an upside down parabola. Where do you think it makes its maximum? by symmetry, very nice, at 1/2. So what can you say? What would you say about P equals 1/2? What would you say about P equals 1/2? Most what? Right. Maybe the scenario with the most randomness, with the most, maybe with the highest entropy, if you heard the term entropy before. So this is a special point. P equals 1/2. P equals 1/2 is the P where a Bernoulli random variable reaches its maximum possible variance. Okay? So in this example, the probability of rain being 50% would give us the highest variance for the number of rainy days in the month of April. Okay? So we'll use this observation. Okay, what is the value here? 1/4. So the variance of a Bernoulli random variable is always less than or equal to 1/4. 1/4 is the largest possible variance for a Bernoulli random variable. So let's just say this is less than or equal to 30/4, which is 7.5. Okay? What is the expected number of rain days? 30p. Okay. So when p is 1/2, the expected number of rainy days is 15, but the variance is 7.5. Okay? The variance is half the expectation in that case. Okay. Any questions? Okay. Let's move on to the next example. So the next example is actually an important observation that I think, let's see, we've already made this observation here, but we're doing this example to really understand what we observed. Okay, show that when the expected value of x times y is equal to the product of the expected value of x and the expected value of y, then the variance of the sum is equal to the sum of the variances. Now, this identity, okay, does not imply independence. This identity is true whenever x and y are independent, but in general, independence is not necessary for this to happen. Now, sometimes this is called linear, x and y are linearly independent in this case. Okay, so how do we show this? Basically, we already shown it here. If you look here, when this term is 0, the variance of the sum is equal to the sum of the variances. Now, this has another name. When expected xy is equal to expected x times expected y, the random variables are said to be uncorrelated. Okay? So uncorrelatedness is implied by independence. Okay? Uncorrelatedness is necessary for independence, however, is not sufficient. So let's do another example to maybe show this fact. Okay, so let's do the following example. Okay. X and y have the following joint PMF. -1, 1, 1, -1, x and y. And all the points are equally likely. Okay? 1 over 4, 1 over 4, 1 over 4, and 1 over 4. Okay? Now let's compute the expected value of x. What is the expected value of x? 0. It's quite obvious, right? Because at these, for these points, x itself is 0. For this point, x is 1. For this point, x is negative 1. But the probabilities of these points are equal. Okay? So clearly, the center of gravity with respect to x is at 0. Okay? Expected value of x is 0. How about the expected value of y? By symmetry, that is also 0. Okay? How about the expected value of x times y? X times y. X times y is 0 at this point, 0 at this point, 0 at this point, again 0 here. Right? X times y is always 0 for all of these points. So the expected value of xy is again 0. So this is satisfied. Expected value of xy is equal to the expected value of x times expected value of y. The two random variables are uncorrelated. Uncorrelated. Expected value of xy is equal to expected value of x times the expected value of y. Are they independent? Who says no? You say no? Okay. Who said no? Who says yes? Yes, please. Huh? Why? Don't you have enough information to determine this? Do you mean you can't determine this just by inspection? How do you know they are independent? Okay, so that's exactly the point I'm trying to make. This is necessary but is not sufficient for independence. Okay? So this basically does not imply independence. And this is exactly a counterexample to show that this is not sufficient for independence. Let me explain why these are not independent. X and y are not independent. Counterexample, you just need one counterexample to show that this is not, independence doesn't hold. Look at y equals 1. When y is 1, x can only take the value 0. But in general, x can take the values -1, 0, and 1. Okay? So the marginal distribution of x is different from the conditional distribution of x conditioned on y. Let me write this down. Px of, let me say, Px of 1, for example, is equal to, what is the probability that x equals 1? 1/4, right? Now, what is the probability that x equals 1 given y equals 0? I'm sorry. Yeah, that's fine as well. When y is 0, we're here. Okay. And with probability 1/2 x is equal to 1, with probability 1/2 x is equal to -1. Okay? So this is equal to 1/2. Oops. Okay. This is the probability that x is equal to 1 given y equals 0. The probability that x is 1 given that y equals 0 is 1/2. Do you agree? Let me clarify the notation for you again. P x given y, x given y. I'm evaluating this at y equals 0 and x equals 1. Right? What do I get? Pxy, 1 given 0. Okay. What is this probability? 1/2. If you want, let's compute this probability the long way. This is Pxy, x given y, I'm sorry. This is the joint PMF at 1, 0 divided by Py of 0. What is the probability that y is 0? Exactly, 1/2. So what is the joint probability at the point 1, 0? 1/4. Right? So this is 1/4 divided by 1/2, which is 1/2. Okay? But we also obtain this by inspection. Okay? On the other hand, the unconditional PMF of x at 1 is 1/4. Okay? So this shows us that conditioning on y changes the distribution of x. If you want to use a counterexample that shows that Pxy, xy does not break into Px of x, Py of y, let's do that with another point. Pick a value for x. Pick a value for x. Okay. Maybe different value. -1. Okay. So let's do that at x equals -1. And y is what? -1. So let's compute this at x equals -1, y equals -1. What is that? Tell me. What is the probability? Yes. What is Px of -1? Px of -1, let's see. 1/4, yes. Because there's only one point where that happens. What is Py of -1? 1/4. The left-hand side is different from the right-hand side. If x and y were independent, the joint PMF would have had to break into the product of the marginal PMFs. It does not, which shows that they're not independent. Even one example like this would have been sufficient. Okay, but we showed 2 examples. Okay? By the way, this does not have to be violated at every point of the PMF. Okay? In this case, it is violated at every point for this example. But in general, it doesn't have to be violated at every point. Even if it's violated at one single point, it's enough to conclude that they are not independent. Okay. Any more questions? Is it clear? Yes, please. Now, let me remind you something. Let me remind you. Okay, I'd like everybody to pay attention to this. Let's consider P x given y, x given y. What is this? This is the conditional PMF of x given y. Okay? Now, by definition, this is Pxy, xy, divided by what? Py of y. Now, when x and y are independent, this numerator breaks down into a product. Product of what and what? You tell me. Selin. This breaks down into Px of x times Py of y, right? And in the denominator, we have Py of y. So what happens, Selin?
Then we have Px of x.
Exactly. Py of y is cancelled, provided, of course, this is not different from 0. Okay? And we get Px of x. Now, do you see this, the marginal, the conditional being equal to the marginal is a direct consequence of independence. Okay? It makes a lot of sense. Because if x is independent of y, if you give me y, I don't care. It doesn't tell me anything about x. Okay? Px given y is the same as px. Okay, I used that here. I used this to just show a quick counterexample. Since px given y is 1/2 and px is 1/4 at the point x equals 1, this shows that x is not independent of y. Okay? Is it clear for everyone? Okay. So, we already said this. Let me reiterate. We'll, in fact, properly define correlation later in the class. But in general, when this holds, the random variables are said to be uncorrelated. Okay? Uncorrelatedness does not imply independence, but independence implies uncorrelatedness. Okay? Now, we said that variance is not linear in general, and variance of the sum of random variables is not in general equal to the sum of variances. But remember that expectation is always linear, okay? And this does not need any other conditions like independence. Okay? Example, the number of email messages I get every day is Poisson distributed with mean 10. Okay? Let L be the total number of email messages I receive in a week. Compute the mean and variance of R. I would like you to think of this example on your own, and let's solve it together after the break. Okay, so I would like you to have a chance to think about this before we do it in class. Okay? Let's continue after the break.